All right, here are solutions for Ohm's law. As always, my recommendation to you is to go ahead first and work out the worksheet, then look at these individual solutions. So let's jump in. Right now, list 2 things necessary for current to flow and describe what each one does. The first thing we need is a complete conductive path. And the other thing we need is voltage or something to push. Those charges. So that complete conductive path it provides free charges. So if we think about conductors, they all have that sea of electron. That means there's one free electron per each atom. It's allowed to move. That's what the complete conductive path does. It gives us those free charges, and that complete conductive path gives the charges a place to go. That's really important too. If it's not complete, we can push those charges, but if they can't move, they won't move. And then in applied voltage, this provides the push. This is the thing that's going to move the charges. If there's no applied voltage, then there's nothing that's going to be able to push them at all. What's the definition of an electric current? An electric current is the charge per unit time moving through a place in a circuit. And so if we look at current, that's going to be the change in charge over the change in time. Current is measured in amps. And if we look at the relationship we just wrote down, 1 amp is 1 coulomb per second. Electric potential, this is stored energy in a battery. It pushes charges. And then the word that we use for this, the word that we use for this is voltage. That's what electric potential is. It's voltage. 1 volt, since it's stored energy, it's stored electrical energy, is 1 joule per 1 coulomb. Yeah, voltage is energy per unit charge. That's how we sort of calculate that. A conductor a conductor is a material that allows charge to move easily through it. That's what a conductor is. In general, what materials make good conductors? Metals. Metals make really good conductors. And the reason they make good conductors is metallic bonding. We have 3 electrons per nucleus. Those free electrons make up the sea of electrons that gives us charges that can easily move. If we bump one charge, it bumps another charge. It's great. What are the 2 best? Right now, our 2 best conductors are silver and gold. Superconductors Superconductors are materials with zero resistance. Semiconductors are materials with special electric properties that allow them to do really fun things with electricity. Semiconductors, they kind of conduct electricity under certain circumstances in certain ways. And because of those special properties, that lets us do things like build computer chips out of them. You can set the voltage that's going to allow to conduct electricity. They're very complicated, but they're great. Use the fluid flow analogy to illustrate what happens when a light is connected to a battery with wire. The way that I like to think about it is we have a battery, and it's kind of like a pump. And then we have a wire coming out of that battery. And then the wire falls down the light bulb. This is where the light bulb is, and it comes back. And so with our fluid flow analogy, we've got water. The battery pumps the water up. So the battery pumps the water up, and then it gives it more energy. So up here, and then at the light bulb, it falls through the bulb and loses energy. And that loss of energy is what we see as light. Now it's heat and light coming out of there. And then it starts and flows back through again. Resistance is a material's ability to impede or make it hard so it's abilities material it's a material's ability to impede charge's movement. Basically, it pushes back against the voltage on the charge. What's the unit for resistance and how it's defined? How is it defined? So resistance is an ohm. So we have 1 ohm. And resistance, well, an ohm, if we look at Ohm's law, I guess, is defined by volts per amp. But really, if we want to look at resistance, resistance is the resistivity of an object. So that's a material property times the length divided by the area. If you're asked, that's probably what you need to go with. What do resistors do when connected to a circuit? They still provide a conducting path, but they reduce the current and dissipate energy. Those are the two things they do. They reduce the current and they dissipate energy. What factors influence the resistance of a resistor? This is where we use resistance is the resistivity times the length divided by the area. So our three factors are the resistivity. That's the stuff in the way. More stuff, more resistance. The length So the longer the thing is, the more length, the harder it is to press charges through. So that means we have more resistance. And then the area, if we have more area, it is easier to move charges. How do you find the resistance of a resistor from a potential versus current graph? If you look at a potential versus current graph, you have voltage versus current, and then you have a slope. Well, from Ohm's law, we know that voltage is equal to current times resistance. That's my Y value. That's my X value. So that's my slope value. So what we can say resistance is the slope of a potential versus current graph. That's how we would find that. From a potential versus current graph, we'd find the slope. All right, so a student uses an ammeter and a voltmeter to measure the resistance of an unknown resistor R by varying the electric potential across it and measuring the resulting current. Draw the circuit showing how the resistor should be connected to the voltage source, including the ammeter and voltmeter, to measure the potential and the current. Okay, so here's our voltage source. That's a battery. And then here's our resistor. So if we want to measure the voltage, we want to look at both sides of that resistor. So we're going to put the voltmeter around the resistor. And if we want to measure the current, what we want to do is get in the way of the current. So we'll put the ammeter in line in our circuit. We have a complete circuit. The ammeter is part of the circuit. The voltmeter is part of the circuit. We have a complete conductive path through the ammeter. But the ammeter is going to tell me the current going through the resistor. The voltmeter is going to tell me the voltage going across it. The student applies a potential of 8 volts and measures the current to be 4 amps. Calculate the resistance. Okay, well, we have the potential. That's our voltage. We have our current. That's I. We know V is equal to IR. So our resistance, if we plug our numbers in, 8 volts equals 0.4 amps times the resistance. So the resistance is 8 volts divided by 0.4 amps. The resistance comes out to be 20 ohms. How much power is dissipated by the resistor? So we have all of these things. We have the voltage, we have the current, and we want the power. Well, we know power is equal to current times voltage. So we have all those numbers. So it's 0.4 amps times 8 volts. And so my power comes out to be 3.2 watts. How many coulombs of charge pass through the resistor in 1 minute? So we want to know the Q, and we have our time here as 60 seconds. That's what 1 minute is. So from our definition for current, current was change in charge over change in time. So 0.4 amps is equal to the change in charge over the time of 60 seconds. So my delta Q is 0.4 times 60. So my change in charge during that time comes out to be 24 coulombs worth of charge moving in that time, which is a ton of charge. The student increases the potential to 10 volts. Okay, so what's interesting about this is that the resistance stays the same. It's a property of the resistor. So my resistance is still going to be 20 ohms. So if voltage is current times resistance, I have 10 volts, and that's equal to the current times 20 ohms. So that current ends up being 10 volts over 20 ohms, 0.5 amps. Now, how much power is dissipated by the resistor? Again, power is current times voltage. So I know that my current is 0.5 amps and my voltage is now 10 volts. So the power being dissipated across this resistor is 5 watts. So there's more power coming off of it now. The student is doing a lot of stuff to this thing. The student adjusts the voltage source until we have 2 amps of current. Calculate the new potential. So here's my current. The resistance is still 20 ohms because we haven't changed the resistor. Adjusting the current and the voltage doesn't change the resistance. That depends on the resistor itself. So my potential, V is IR. Well, we have the current, 2 amps. We have a 20 ohm resistor, and so it's 40 volts. And then how much heat is dissipated by the resistor in 1 minute? Okay, so for this, to get heat, Q, I don't want to use Q again. So heat is power times time. Energy is power times time. So I have 60 seconds. But I need power. So power is current times voltage. So power is 2 amps times 40 volts. So that's 80 watts of power. So I gotta plug that in here. So my heat is 80 watts of power times 60 seconds. So my heat comes 4,800 joules worth of heat from that 80 watts in 60 seconds.